Welcome to the video. In this video, we are going to look at the second section of chapter 23, and that is the Gauss Law. If you look at the bottom of this screen, you can see that there are two equations. We are always going to use the second equation, because in that second equation, the integral is just the definition for the electric flux. Now, on this page, in addition to the two equations, there are a couple of paragraphs along with a rather complicated diagram that help explain what Gauss' law is. We are going to skip the diagram for now and go to the next page. This next page is where the textbook combines the Coulomb's law and the Gauss' law, and we are going to take a closer look on this page. If you look at that second equation, and once again recognizing that that integral is just the electric flux, then what Gauss' law says is that if you take the electric flux and multiply it by epsilon naught, and here we want to recall that epsilon naught is just a constant first introduced in chapter 21. So if you take the electric flux and multiply it by epsilon naught, then the product will be equal to the QENC. And what that QENC means is the total charge enclosed by the Gaussian surface, as you can see here. While we are looking at the equations, let's recall that little circle in the integral indicates that the Gaussian surface is a closed surface, and the integral is meant to be done over the entire Gaussian surface. Let's now take a look at this diagram at the upper right hand corner, where there is a charge Q surrounded by a spherical Gaussian surface. The charge is positive and is located at the center of the Gaussian sphere, for which the radius is r. What we need to do is to calculate the total electric flux. I'll do that at the bottom of this screen. Let's first recall the electric field created by a point charge. You will want to recall that in this definition, the charge Q can be either positive or negative. And a unit vector r hat is a vector that points away from the charge. So that if the charge is positive, the electric field points away from the charge, and if the charge is negative, the electric field points toward the charge. In the current situation, the charge is positive, so the electric field points away from the charge along the radial direction as shown in the diagram. We should also recall, this time from geometry, that the radius and the circumference of a circle are always perpendicular to each other. In theory, it is the tangent which is always perpendicular to the radius. But if you blow up the diagram and take the limit, then you will see that it is a valid approximation, that the radius and the circumference are perpendicular to each other. By extension, in 3D, we will say that the radius is perpendicular to the spherical surface. Let's now go back to the diagram and look at just the small surface element, which I will reproduce at the bottom. We can see that the electric field is pointing outward and is perpendicular to the spherical surface. The situation is very similar to an old friend of ours, and that is this diagram. The part that is important to us is reproduced here. Even though they look different, they share two important characteristics. First, the electric field is pointing outward. Second, the electric field is perpendicular to the surface element. Therefore, we can conclude that the electric flux for the surface element is just E the vector dot dA the vector. And since the direction of the surface element dA is also pointing outward, the two vectors E and dA are parallel to each other. The angle in between them is 0, resulting in a dot product that is just the product of the two magnitudes. Notice that at this moment, what we have on the left-hand side is the differential electric flux, which is a scalar, and what we have on the right-hand side is also a scalar. Let's again go back to the diagram at the upper right-hand side. And we want to see that our calculation for the differential electric flux is the same over the entire surface, because no matter where or which surface we looked at, the two outstanding characteristics will always be true. First, the electric field is pointing outward, and second, the electric field is perpendicular to the surface. So we can perform a summation of the electric flux over the entire surface. And since in our case, a summation is just the same as an integral, we can do an integral over the entire surface. We now want to go back to that upper diagram one last time. We want to recall that the electric field is supposed to be calculated at the point of interest. And in the current case, the point of interest is on the surface. Since the electric field is only a function of radius r, and r is the same on the entire surface, the electric field is the same all over the surface, which of course means that the electric field E is a constant all across the surface. And if that's the case, we can move the E outside of the integral, and let's put it in the front. And that integration over dA should be just the entire surface area. Let me take a moment to add a little circle back to the integration sign to indicate that the integration is done on a closed surface. And all that we have to do is to recall from algebra, the surface area of a sphere is equal to 4 pi r squared. And we are now ready to apply Gauss' law, which says if we take the electric flux and multiply it by epsilon naught, it should be equal to the total charge enclosed in the Gaussian surface. For the current situation, we have already calculated the total electric flux. So let's take that and multiply it by epsilon naught. And of course, the total charge enclosed is just the Q itself. So this one line here is the application of the Gauss' law, from which, and with a bit of algebra, we can obtain expression for electric field evaluated on the Gaussian surface. And not only that, if we look at the diagram, at the upper right hand corner once again, and we can see that at every point on that Gaussian surface, the electric field is pointing radially out, which corresponds to the unit vector r hat. And therefore, going back to the equation that we just wrote down, we can add a vector sign. And that is the result that we want. And you can see that by applying the Gauss' law, we end up with an expression that is exactly the same as before. Of course, we don't have to derive the same equation twice, but what this example does is to show us that the Gauss' law works on an example that we are familiar with. To recap, the Gauss' law says if you take the electric flux and multiply it by epsilon naught, then the result will be equal to the total charge enclosed. And that completes this video.